To build a machine capable of human-like intelligence, early computer scientists looked inward. They mapped the electrical pulses inside the human head, hoping to reverse engineer the brain's organic architecture. These are biological neurons. This microscopic web of dendrites and axons is the physical blueprint researchers in the 1950s attempted to replicate in silicon. Their first attempt was the perceptron. In this model, incoming signals are assigned a weight and funneled into a central node. If the sum of those signals crosses a specific threshold, the artificial neuron fires. However, these systems lacked a way to learn. Engineers had to manually tune the mathematical weights of the machine's connections, essentially guessing which values would produce the correct output. This manual logic worked for basic mathematical problems, but it struggled with the messy, non-linear patterns of the real world. When asked to process overlapping categories or complex visual data, the simple perceptron failed. This inability to handle complexity stalled progress for decades, leading to the first AI winter. It became clear that for neural networks to scale, researchers would have to stop hand-coding the rules and find a way for the machine to adjust its own parameters. The solution required stacking these artificial neurons into multiple layers. By creating a deep network, researchers hoped the system could finally model complex relationships. But more layers meant millions of new weights. Calculating the correct adjustments for every single connection by hand was no longer an option. This landscape is an error surface. It provides a visual map of the network's mistakes. The peaks represent high error rates, while the deepest valleys represent the most accurate mathematical solutions. To find the bottom of this map without human help, networks use gradient descent. It calculates the steepest downward slope at the network's current position, automatically nudging the parameters toward a more accurate result. To save time, researchers often use a stochastic approach, taking randomized many steps to find the valley floor faster. This is coupled with backpropagation, which sends these mathematical corrections backward through the layers to update every connection at once. This automated optimization engine allowed researchers to train networks with hundreds of layers. It effectively ended the AI winter, proving that deep models could learn from their own data. Even with an optimization engine, larger networks introduced a new risk: overfitting. Instead of learning general rules, a model might simply memorize its training data, making it useless when faced with a new problem. To prevent this, researchers use regularization. These mathematical constraints discourage the network from relying on overly complex patterns, forcing it to find simpler, more robust solutions. Training also requires stripping away noise from massive datasets. The network must learn to ignore irrelevant details and focus only on the most predictive features. This diagram shows an autoencoder, a specialized architecture designed for this task. It forces input data through a narrow bottleneck, squeezing out the noise and keeping only the most essential information needed to reconstruct the original. This structural bottleneck forces the model to prioritize the underlying structure of the data. By learning to compress information, the network develops a more efficient way to represent reality. By combining automated optimization with these constrained architectures, the field entered a period of rapid development known as the deep learning revival. Convolutional neural networks, or CNNs, led the charge in computer vision. They gave researchers a way to process visual information in a specific, layered hierarchy. A CNN scans an image in stages. It identifies simple edges in the first layer, builds them into shapes in the next, and eventually recognizes entire objects in the deepest layers. This hierarchical approach allows the machine to categorize complex organic subjects. Because of this, recognizing a cat became one of the standard tests for early vision models. Language underwent a similar transformation through distributed word vectors. Rather than treating words as isolated entries, this model assigns them spatial coordinates. Words that appear in similar contexts in human language are mathematically clustered together. This spatial arrangement allows the system to calculate the distance between concepts. It enables the model to identify word relationships and analogies based on statistical patterns found in massive amounts of text. We have moved from manually dialing single artificial neurons to building architectures that can navigate language and vision. The current challenge is taking these models a step further, transforming them into AI agents capable of reasoning and acting autonomously in our world.